Welcome to today's webinar. This webinar is titled The Power of Echo Project GPR Software. My name is Greg Johnston, and I'm a product manager with Sensors and Software, and I've been with the company for 32 years. The agenda for today, we are going to talk about, we're talking about software mainly, but it's software that is plotting data. And so I want to start off talking a little bit about data collection, GPR data collection, and the various ways to do that. We'll talk very briefly about exporting the data from the data logger to a PC. And then we'll get into talking about Echo projects, specifically visualizing data, so plotting data in various ways, understanding the data by adding interpretations to it, and reporting the data, outputting files like PDF files, Google Earth files, 3D, various outputs that are deliverables based on your GPR survey. And I'll also talk a little bit more about some other output files that may be useful. And we'll talk about a specialized module that is available in Echo Project. And then at the end, hopefully we have a bit of time for questions. I'd encourage you to add questions to the Q&A if you can. If that fails, put them in the chat. We have some people monitoring who can answer your questions, and any outstanding questions at the end, I will answer live. And then at that time, we can also unmute you and you can ask questions at that time. So that's our plan over the next hour or so. Okay, so Echo Project software plots GPR data. So to properly set the stage before we get into the details, it's important that we talk a little bit about data collection. Broadly, there are two types of GPR surveys, these GPR reflection surveys. The first is line scans, as shown here. The GPR system is moved from point A to point B, and GPR traces are collected at equal intervals in between, generating a cross-section of the subsurface. The second type of GPR survey is a grid scan, where a gridded area is scanned with multiple parallel grid lines. In this example, this gentleman is collecting a small 5 meter by 5 meter grid, and we're going to watch him collect the first few lines. And you can see on the screen, this is what you see in real time as you're collecting the data. As you push it along, you see the GPR symbol moving along, and then at the end of the line, it automatically stops because the odometer knows that it's moved 5 meters and it will automatically stop the line. Please note that he's not collecting data when he backs up. It's only when he's pushing it forward. So each line in the grid is actually a separate file. Another way to collect data over an area is to combine line scans and grid scans and collect a pseudo grid by walking back and forth on one line scan. So doing it this way, you're essentially mowing the lawn. You're trying to cover the area with a nice tight line spacing so that we can image what's in the subsurface. So this method relies on an accurate GPS for positioning, and it should only be done in areas where the GPS is not going to glitch. So doing it under tree cover is not a good idea. Doing it around tall buildings that block satellites is not a good idea. You really need to have the maximum number of satellites so you get the positioning accurate. Keep in mind that you can start the data processing and reporting process by adding field interpretations to significant targets you see while collecting the data. So you can see in this example here, we're marking the top of hyperbolas, which are targets that they're interested in locating. And so we can put them in different colors. So we can put a pink color, and I think he's switching the color to blue and then putting a dot on the other one because they're two separate objects. So you do this with our products by simply touching the screen at the location of the target of interest. Doing this in the field will pay dividends later when we open the data in the Echo Project software. So here's an example of this. Note that as the operator is collecting the data, they're pausing for a second to add a point interpretation to the top of the hyperbola that they see with every pass over the top. This is a great way of tracing a linear object like a utility. You see, unlike the last screen where he was doing a fairly tight line spacing, this is a wider line spacing, a couple meters apart, but it allows you to, if you keep seeing the same hyperbolic response over and over with each pass, it's a pretty good assumption that it's going to be the same object. And if you watch the screen here as it updates, you're going to see the map view image that's created and how the pink dots that were added, the pink interpretations added to the data, line up in a straight line. So right here, you can see the path and you can see the dots that line up that shows a linear utility. So that's another way of collecting GPR data and adding interpretations out in the field. We have a feature in some of our GPR products, the LMX products, called split view. And what split view does is it shows half the screen as a cross section and half the screen as a map. And of course, you can only do this with a GPS. And what it does is it makes it easy to follow targets with each pass as you cross over them, because you can add interpretations and see the dot on the screen and confirm that the dot is lining up with the previous dots. Because typically utilities, linear objects are going to be linear or at least smoothly changing. So if you see that it suddenly jumps 2 or 3 feet away, it's probably not the right object. In fact, if you watch this video, of course it's sped up, but if you watch this video, you can see that he's actually making some mistakes, and he's putting a blue dot on one and a pink dot on the other, and he's had to make a couple corrections to make sure that the colors line up. Now, in the end, we have 2 utilities that have been traced, and it's interesting that we're able to follow them even though they're crossing one another. And so in this case, it was fairly obvious. One of them was shallow, one of them was deeper. So with each pass, he could tell which one was shallow, which one was deeper. So split view gives you the possibility of following targets like this, either one or multiple targets with confidence. Also note that as you're collecting data, one of the options with our systems is the camera button. And pressing the camera button will save the current image on the screen to a JPEG file, which is saved with your project data. And this is a very quick way to create a report, is screen captures of significant data or interesting data out in the field. So keep that in mind, that as you're collecting the data, you can write a lot of your report by clicking the camera button and saving those images. And the last thing you're going to do out in the field is make sure you take photos. That becomes valuable when you're generating your report at the end. So pictures of action photos of people collecting the data, but also you want to take pictures of areas where you've collected grids or pseudo grids, because I'm going to show you a capability of adding depth slices onto photographs. And so make sure you have those photos available to you when you get back to the office. Now, of course, the last thing we're going to do once we've finished our data collection is we're going to transfer the data from the data logger by putting in a USB stick, saying yes, download the data to the USB stick, and we're going to copy it over onto our PC and get started. So a little brief introduction to collecting data. So now let's look at taking that data into the Echo Project software and the types of things that we can do with it. Now here's a screen capture of what the Echo Project screen looks like when you open up data. And there's everything you need to work with the GPR data is in one view available to you. Let me just briefly go through. So over on the left is the GPR lines that were collected. And those could be individual lines like line scans. Those could be a grid. So you might have a grid that might have 20, 30, 40 lines in it, all marked with X's and Y's in them to help you differentiate them. In the middle there is the line preview, which when you click on a line name on the left-hand side there, it will appear in the line preview. And you can scroll into that. You can scroll back and forth, zoom in and out, that sort of thing to have a good look at the data. You also have a window called Map View, and Map View is exactly that. It is a map view of your survey site. So in this example, you can see that the lines that were collected were that pseudo grid type data collection, zigzagging back and forth on a very tight line spacing here, covering a larger area to look into the subsurface. And the last window there is the data layer window, which allows you to turn things on and off. Sometimes there's too many elements in the display. You might have GPS and interpretations and flags and depth slices and all these things that are available. And there's too much. You want to simplify the image by turning some off before you save it. You save an image that's going to end up in your report. So that's strictly to help you, assist you with the interpretation. And that's kind of, it in a nutshell. Is those elements are used to use the Echo Project software. Now, the catchphrase we use for Echo Project is visualize, understand, report. And those are the three things that it does. It's designed to visualize your GPR data in various ways, allows you to look at it so that you can understand it, add interpretations to the data, add your insights to the data, and then finally report those. And a report can be a PDF output, but it also can be other types of outputs like CAMZ files, Google Earth files that you can put into GIS software, CSV. There are quite a number of files output. So they're not always strictly a report, a written report, but they are report type files. Okay, so let's talk about visualizing GPR data. You've been out to the field, you've collected your data, you now want to analyze it, and we're going to start by visualizing it. There's really four ways to visualize GPR data. The most basic GPR data is a single trace, shown here on the left side. A trace is a recording of the signals that arrive at the GPR receiver after the GPR transmitter has fired. When the transmitter and the receiver are located at one position, it is 1D data. Next to that, if you have a series of traces, all one after the other, at different positions but with equal spacing, that creates a GPR line, which is a 2D vertical cross-section of the subsurface. When multiple GPR lines collected together cover an area, either collected as a grid or as a pseudo grid, as I mentioned earlier, they can be combined, processed, and plotted as a series of depth slices. And a depth slice is a 2D horizontal map of the subsurface at a specific depth. The last type of plot on the right is a 3D volume. And so grid data, GPR grid data, can be plotted in as a cube or a volume in 3D, so we can spin it around, we can slice into it, we can peer into it. And so these are really the four ways that we can plot GPR data to analyze it. And Echo Project provides all these types of plots, as I will show you. But I'm going to skip traces for now, and I'm going to start with cross sections. So in Echo Project, you have the ability to take your line scans and plot them onto the screen. We have different color palettes. You can choose whatever color you want. And what you're showing is the extreme negative signal to the extreme positive signals in different color formats. We can also change fonts, and as you see here in the top blue one, we can even plot data in wiggle trace plots if you're old school. Now, most of you are going to know that as GPR signals travel into the subsurface, they gradually get weaker and weaker because they're getting absorbed by the soil. They don't travel forever. Sometimes they don't travel as far as we want them to, but that's physics for you. Therefore, it's almost always necessary to apply an amplification to your data called gain. So we're gaining the data especially to amplify the weaker signals at depth. And so the plot you're looking at, this is the same section plotted with 9 different gains, from a very, very weak gain at the top left to a very strong gain on the bottom right. And those two extremes look bad in various ways. The top left is very blank. It hasn't had enough amplification applied to it. The bottom right is too much gain. Everything, all the signal has been amplified so that it's very, very busy looking. It's very difficult to interpret the data. So the correct gain in this case is somewhere in between. So the one right in the middle is probably a nice looking gain. That we would probably use that when we started to interpret our data. But the problem is gaining the data can be challenging, especially if you're new at ground penetrating radar. So you want the best possible image before you start interpreting the data. And so you want to make sure it's properly gained. But as I say, gaining can be tricky because there's really 3 parameters that need to be adjusted: the start gain, the attenuation, and the maximum gain. And so that can take a little bit of fiddling to get it right. Well, I'm happy to say that in the new version of Echo Project, which was just released early May, we have a new and improved auto gain that automatically optimizes those 3 parameters so that GPR cross sections always look their best and are ready for interpretation. So we did have an auto gain before. The auto gain before worked about 50% of the time. So a lot of the time you end up fiddling with the data to try to make it look right. And we don't want people spending their time trying to optimize the image. We want them interpreting their data. And therefore, really happy with this new auto gain, which we've been testing for almost a year now. And in my experience, it's working about 99% of the time. It's very rare that I have to adjust the gain without beyond the auto gain, which you do have the ability to do. We're not taking that from you. If you do want to change the gain, you can do it. But if you're new, the auto gain works very well most of the time. The other thing we typically do with GPR cross sections is we apply what's called a background subtraction filter, or you'll see it in our software just called filter. And because sometimes GPR lines can have horizontal banding, and it's called system noise that you can get. And system noise from cables and that sort of thing can create bands in your data. And it's not real subsurface reflectors. It might look like a reflector, but when it's absolutely dead flat, you should always be suspicious. And I've talked about that in previous webinars. And so you have to be careful not to interpret those. I've watched people interpret these perfectly flat bands as being, the bedrock surface that they're looking for, and going, no, wait a minute. You should always have a healthy skepticism of your data. Is that a real reflector? And things that are absolutely dead flat in the data are not typically real reflectors. And so it's fairly routine to apply a filter to remove those. And that's called the background subtraction filter. It's also desirable to remove the flat-lying signals at the top of the GPR cross-section. So let me turn that on. So this is showing the filter as it's applied at various levels here. So the signals at the very top, when the filter is set to 0 here, those at the very top, you see these strong black and white signals, and those are the direct arrivals. That's the energy that travels directly from the transmitter to the receiver in air, but also at the ground velocity as well. So they're called direct air and direct ground signals. And that energy can mask shallow reflectors. And so it's useful to remove it so that you can see these very shallow objects. And if you watch this, look at as we apply the filter stronger and stronger, you start to see some of these point objects with hyperbolic responses very shallow that were masked by the direct arrivals. And then sometimes as well, there are real reflectors in the subsurface that are flat lying. And if we're looking for point objects that produce hyperbolic responses, then we might want to filter out the soil layering and that sort of thing that we see in the data. And so those are all reasons why we apply background subtraction filter. And so you'll notice that the filter gets more and more severe. We can shorten the filter. The shorter the filter is, the more severe it is with the data. So applying a harsher filter will remove more and more of the flat features in the data. But hopefully you've noticed now there's a few objects here that were difficult to see without the filter. And once you apply the filter, I gain a lot more confidence on certain hyperbolas that I was really wondering about before the filter was applied. So that's a standard part, and it's easy to do with the Echo Project software. So let's talk about elevation correction. If you take data out of context, you can very easily misinterpret it. So if I'm looking at this cross section and I say, oh, that's an interesting reflector right there, this one that's kind of zigzagging through, looks like it goes shallow and then it kind of dips into a pit and then comes up. And I might come up with an interpretation of what that is. But one thing I should probably do is apply the elevation correction to the data. And so when we apply the elevation correction, this is actually what the data looks like. And we can see that particular reflector that I thought was undulating is actually flat lying. And in fact, the GPR was collected sort of down a hill into a low area, up a hill, and then back over on the other side. And that explains the shape of this reflector that was flat, but doesn't look flat when you look at it without the elevation on it. And so that's one of the advantages of having GPS as well, is you get that elevation information that you can use to apply an elevation correction to your data. Again, a standard part in the Echo Project software. Here's another example. I'm going to show this one a bit later as well, but I wanted to show you now. This is a very spectacular GPR cross section, 1,100 meters long, left to right, 50 megahertz. Collected, we are seeing signals down 50 meters, and this is not typical. This is an extremely good environment for ground penetrating radar, very low electrical conductivity, and it's allowing the signal to travel great depths into the ground. And if we apply the topographic correction, like the last one, you'll see that it actually looks like this. And a lot of those reflectors that looked like they were dipping weren't dipping. It was simply because part of the section went up, I think, on a sand dune or something, and then came down on the other side. All right. So again, the point is you can see how the elevation correction improves your data and gives you the best place to start interpreting it. Okay, the last thing I want to talk about, cross sections or lines, is the ability in Echo Project to right-click on any response in the GPR cross-section and find that spot on Google Earth. And so this will go, you'll show this again. So this animation shows how, providing your GPR data was collected with GPS, you can find the location of that target of interest on Google Earth simply by right-clicking, selecting the option to go to Google Earth, and then doing the Google Earth fly-in. And in this case, we're flying onto a street in downtown Phoenix, outside the convention center, where I think I was doing a course a few years ago. And we can see the exact point where that hyperbola is. So seeing your GPR data in the context of where it was collected, like Google Earth, greatly assists interpreting the data correctly. Okay, now that we've seen the types of things you can do with GPR lines, so let's move on to the next type of plot called depth slices. So here's an example. We're going to start off with a grid. So you see that somebody collected a grid that is approximately 25 feet by 25 feet or so. And so we're going to use those lines to generate a depth slice. So here's our depth slice, and it's actually a depth slice animation. So we're slicing down from the surface down into the ground, and this is a utility example. So we're seeing different linear objects at different orientations at different depths as we slice down. Starting at the top now, so we see that one and another one. So this is a pretty complex area. There's a lot going on, and the GPR is getting reflections from all those. We can generate depth slices from the slice view grid option, which is in Echo Project. Here's another example. It's an archaeology example. And notice the change in scale. So the last one was, what, 25 feet by 25 feet. This one is 55 meters by 75 meters. So quite a large area. This is a good chunk of a field. And what we're seeing are the buried foundations of Roman structures actually in Romania. And so a customer sent this to me a few years ago, and it's just fascinating to go down, to watch the depth slices go down through, revealing buried structures of buildings and multiple buildings and foundation walls or fortification walls, this sort of thing. So a lot more stuff than my expertise, but it's a very pretty picture to watch. And you can watch it over and over and see different things every time. And this one, in a nutshell, is the power of depth slicing GPR data. Here's another example from a cemetery. It's a surprisingly common application, is cemetery surveys. Much as you think that, wait a minute, they don't know where the bodies are, a lot of times they don't. Headstones move, headstones get buried, headstones disappear, so they may not know what's located where. And so GPR surveys in cemeteries are commonly done. And so in this example, you see as we're slicing down, we're hitting shallow coffins, and then as we slice down a bit deeper, we see deeper coffins, and then we roll around to the top and go down again. In this area, just to give you a scale, 20 meters by 20 meters. So the next few examples, the previous examples were all grid scans. They were grids collected in the X and Y direction. So now the next step slices are generated from pseudo grid data. That is data collected covering an area with a high accuracy GPS. So you need that in order to position the data. So if you look at this example, you can see somebody collected this area in 2 line scans. They collected one line running in one direction, and they just zigzagged back and forth. And if you look at the edges, you can see the curved path as they go around the edge and then come back. So these lines are probably a couple kilometers long in each direction, but we've covered a very large area to do this. Now let's turn these into depth slices. We can use the slice view lines option in Echo Project to turn this into depth slices. And so now here's our depth slice from this area. And what I would caution is, I would always say, if you're doing this type of data collection, do not interpret things right on the corner where you've kind of picked up the GPR and turned it around 180 degrees. You're always going to see odd edge effects there. So I'd be very careful about interpreting too close to the edge. But when we look in the middle, we see all kinds of interesting things. We've linear things that are probably utilities running through at various angles. We've got these point objects, which we actually figured out, this isn't too far from our office, and we figured out that these are actually tree root remnants. So they're the root mass from trees that had been cut down years ago. So there's no visibility on the tree anymore. You don't see the trees, but the roots are still there, gradually rotting away, and the GPR picked that up very well. So all those black dots are actually clumps of tree roots. Here's another random walk, and I dare say this almost isn't this is random walk. This isn't a pseudo grid, it's more of a random walk. You can see that they really just walked all over the place to cover the area, but it still works. It still works. As we slice down through, you can see 3 utilities. There's actually 2 here running in this area. There's 2 at different depths, one there. Actually, here's the shallow one there, and then the deeper one here. And then if you look over in this area on the left-hand side, there's one that runs right through there. So they're picking up utilities with this random walk. So once you have depth slices, one of the best ways to display them, to convey the results of your GPR survey to your client or your audience, is to use the photo slicer feature in Echo Project. And that's shown here. So we took photos of the site, and now you can superimpose the GPR cross section, or sorry, the GPR depth slice on top of that area. And it's a very powerful way of conveying what it is you found. And so this is the reason why it's important to take photographs of the site, and especially the areas where grids and pseudo grids were collected. Here's another photo slicer example. So a random sort of data collection there superimposed where the people were collecting the data. This is actually a karst area, the area with caves. And so the bright spot there, the strong red reflection, is interpreted as being a small cave in the area. Another example of a utility collected a pseudo grid across this field, and you can see the red utility running across the field, very much in context and very easy to communicate the information to people who are non-GPR experts. Different example, high frequency GPR collected on a concrete floor in a warehouse. And so you see what you expect. We're expecting to see rebar, and you can see the rebar running through in 2 directions. If you look closely, you can see a patch of rebar that was, it looked like the concrete floor was ripped up, and they replaced the rebar because they have a very different character to the other rebar. So good information for people who are interested in what's going on with their concrete floor. All right, let's move to the type of plot. It's one of my favorite types of plots, and it's a great way to analyze grid data. It's to use a feature called 3D preview, which is a combination of depth slices and grid lines. And you may have never seen this type of display before, and it does take a bit to get your head wrapped around it. But once you understand what you're looking at, I think it's the best way to review grid data collected with GPR. You're essentially looking at 3 sides of a block, of a cube. So imagine the depth slice that we're looking at, the blue and red section here, that's like looking top down. That's the map down image that we're looking at. Those are the depth slices. The cross-sectional image on the side is like looking at that same block on one side. And so this specifically are the lines that are running in the X direction. So those are the X lines. And the line that is on its side is the Y lines. So those are lines that are running in the Y direction, but we're plotting them so they're parallel to the crosshairs here. And so you can see the crosshairs actually on the edge. And so once you kind of follow what's going on, you can understand how hyperbolas attach to linear features in the depth slice. So for example, if I'm slicing down here, you can see these 2, actually the other element here is the 2 red lines that are the thickness of the depth slice. So a depth slice will actually have a certain thickness to it. So you're typically slicing down through the data at, say 4 inches or 10 centimeters or something like that. So in this example, we're slicing down through, and when those 2 red lines intersect with a hyperbola, you're going to see a linear feature in the depth slice. And so we see the one hyperbola on the Y line, and we see multiple hyperbolas on the X line. And as you follow the depth slice down, you can see those utilities appearing and disappearing as we slice through them. So we can also change, you can change the animation to any one of the three. So you can animate in the depth slice direction, you can animate in the X line direction, or the Y line direction. And one of the other features of Echo Project is GIFs. So it will generate GIF animation files. And these are nice deliverables because, again, the software, you don't need any extra software for somebody to plot a GIF file and watch the animation. So your client can take that and watch the animation if it's providing useful information to them. Okay, so now let's move on to plotting a GPR grid data in 3D. So here's a plot. We're going from cross sections, and then we're gonna save a 3D file and then plot it in 3D. So in this particular example, we've got utilities, we've got T-junction of utilities, and then another utility that's running through. And so again, this will circle around. So here we are, we see the strong hyperbolas in the data. And as we slice down, we see different utilities at different depths. That totally lends itself to looking at it in 3D. And when you plot it in 3D, you can see the orientation of the utilities and you see the variation of the depths of them. One's shallower and then the T-junction is deeper. 3D, very nice way to look at your GPR data, but not always the easiest. You have to admit that GPR data often has a lot of clutter to it. It often has a lot of reflectors that are very strong, and therefore it makes it difficult to differentiate so that you only see the object in 3D that you want. Usually there's other things around there that have the same amplitude or the same signal strength, and so it could be difficult to view. So in some cases it works very well, but in other cases it may not look so good. Another example of 3D. So we're taking the cube, and one of the neat ways to go through it, remember the cube of data that you've collected is really GPR signal strength at thousands or actually millions of different points at different positions, different depths, and they all have different amplitudes. And in plotting in 3D, one of the things you can do is you can say, all right, make all the amplitudes that are weaker than this invisible. And that's what we're doing here. So we're only showing the most reflective objects in that cube. And if that's the object you're looking for is very reflective, then we've got a great display of it. Geological example, so that the geologists are happy here. So looking at GPR data in 3D format with geology. So in this case, we're looking at, I think it's sand dune data, but we certainly see dipping reflectors in here and other more flat-lying reflectors. And when we look at it top down, we see the strike direction of these various features. And so good way of looking at geology is with 3D. Okay, let's talk about understanding the data. So we've gone through the visualization of the data. So now we really want to pull the information that we're interested in out of the data. Let's talk a little bit about that. One of the important things that we need is the velocity that the GPR signals are traveling in the subsurface. And this is often done in the field, but it can also be done in Echo Project. And the reason why we need an accurate velocity is so that we get an accurate estimate of the depth of objects. But velocity is also very important for depth slices and 3D processing. If we're going to make the best possible images in our depth slice, we need to know the velocity the signal is traveling. And we can do that quite simply in the Echo Project software. The other feature in Echo Project is adding interpretations to the data. So if we see hyperbolas, we might add a point to it. If we see a layer, we might add what's called a polyline to it, a polyline interpretation. We can draw boxes around features that we're interested in. We can add annotations as well. So those are the four types of interpretations that we can add to cross sections, GPR lines or cross sections. But I want to point out that we're not just creating pretty pictures here. Every object that we mark, either with a polyline or a point, has a position. It has an XYZ position. It has latitude and longitude if we were collecting with GPS, so that we can actually place these objects in a world coordinate system. And by adding interpretation to the data, you are saving that position so that we can extract it and use it later on. Here's the data you were looking at earlier with the over the sand dunes data, the 100 megahertz data where we were seeing 50 meters deep. And here's the geologist's interpretation of it. And so the interpretation, they added polylines onto it and said, you know, the upper part is aeolian deposits, and then they think it's barrier bar deposits above here, and then glacial outwash deposits. And then finally down at the bottom, they think this is the bedrock surface. And so they've added interpretations, polyline interpretations to the data. We can also add point interpretations, just like the field interpretations that you saw earlier, touching the top of the hyperbola out in the field. We can do that in lines after the fact in post-processing. So here we have 3 lines that were collected side by side, and we can see the character of certain hyperbolas are similar, and we can match those up. So this one is we marked with a blue dot. This one is a little bit different looking, shallower, different character. We've marked it with a green dot, and this red dot appears here. It's probably just off the edge of this line, and so on. So powerful way of marking where things are. Now, you saw this earlier. You saw this depth slice animation earlier. This was the one. And so one of the things you need to realize is the targets in depth slices are only visible if they have reflected a lot of GPR energy. In other words, they have a high contrast of materials that results in a lot of GPR energy reflecting from them. And that is certainly true for metal objects, which provide 100% reflectivity. But non-metallic objects reflect less energy and don't necessarily show up in depth slices. So how do we get these weaker targets to appear in our map images? Well, we can add point interpretations to them. So just like that previous slide, somebody went through all this data and added point interpretations to all the hyperbolas that they saw. And let's look at the final result of that. So here is a map of all hyperbolas in the data. So we can see them lining up to form utilities. And I think we see a few more utilities than we were seeing just with the depth slice animation. We can also see, remember, this is the one that had the root masses in there, and those are the brown interpretations, are kind of these pockets of root masses. The green interpretations are metallic looking responses that were ringing in the data. And so overall, we get a final map that gives us a lot more detail than the depth slice alone. Okay, we saw earlier 3D plots of GPR data, and as impressive as I think they are, your client could probably care less about them. What does a client want? What do our customers want? They don't want GPR data. They want to know what the GPR found. They want to know the position and the orientation of the objects the GPR survey found. So adding interpretations to your GPR data allows you to extract the information your client is really interested in and plot it. And that's what this example shows. This is actually a new feature in Echo Project V6R2, which came out a couple of weeks ago, as I mentioned. So after you add interpretations, after you add point interpretations to the hyperbolas, which is what we're doing here, we got 2 very characteristic hyperbolas, one shallower, one deeper. We've added a bunch of point interpretations to those. Now we're adding red dots to the deeper hyperbola. And then in the end, the next step, we'll see that in map view here. And then the last step, which is new, is plotting them in 3D. So now we can see the lines line up. We can see that they're at different depths. and we can put axes on them. So this is a nice new feature in Echo Project, and it's really showing the information that your customer is interested in, not just GPR data, because a lot of people look at these cross sections and have no clue what they're looking at. Another new feature is an interpretation on depth slices, and we call them map view interpretations because they're performed on a map view of the data. So we've introduced this new type. So as the user scrolls through the depth slice, each one from a different depth, obviously, if they come across a linear feature in the data, they can draw a line on it. And here we can see this is this gray linear line that was drawn across the red response in the GPR data. In this example, there's another one shown here at an angle, and that one is actually from a different depth. So we're not seeing the response in this particular depth slice. The image on the right here is from a golf green. And the golf green, we're actually looking at the drainage pattern from the golf green. And so again, we've drawn some lines on it. We've drawn some map view interpretations onto it, and we can extract that information from the GPR data. Now here's an animation that shows this process. It is sped up, admittedly. It's shown on concrete data with rebar in it. And so what they're doing is they're putting map view interpretations on the rebar. And then when they're finished putting those on, they're going to slice down deeper. And now we see a conduit running through at an angle. So we put a map view interpretation on it. Now we see other conduits even deeper down. So we put interpretations on those. And then we plot it all in 3D. So we can see what we're really interested in, the targets that are in the concrete. So in this example, it's coming up. So here's the 3D plot. So we see the rebar is the shallow part, and then we get conduits that are interpreted as conduits running through the concrete. So we think this is a terrific way of showing the data and conveying the information that you've found with the GPR. Okay, when interpreting GPR data, the context of where the data was collected is very important. You're going to interpret data collected on a street in a major city differently than data collected in a farmer's field, on a mountain, or on a glacier. Positioning is a critical part of this. We encourage GPR users to always collect data with GPS, but sometimes for many reasons that's not possible. So you may find yourself wanting to position the data in post-processing. In this situation, Echo Project has you covered. You can enter the start and end positions of any GPR line you collect. You can position any grid that you collect anywhere in the world by adding 2 positions or 1 position in a rotation. So this means that we can place our GPR data anywhere in the world as shown here. And those of you will recognize perhaps that this is Stonehenge. And note that the intention is not to be deceitful with your GPR data, but I just wanted to show you what's possible to do with the positioning of your GPR data in the most memorable way possible. Okay, one of the things that's very difficult for GPR practitioners is determining just how deep the GPR signals penetrated into the subsurface at their survey site. The depth of penetration is where the amplitude of the GPR signals have decreased by attenuation down to the same amplitude as the background radio noise level. So in this example, just eyeballing this, I'd call it about 1.75 meters, right around there. So if we're looking for a target at a depth of 3 meters at this site, GPR is not likely going to find it. An estimate of the depth of penetration is important information for me to convey to my client. I have heard cases where the client thinks because they got a GPR scan done and they didn't find anything, that they are safe to dig. And this results in damage to infrastructure that was present but below the depth of penetration of the GPR. So it's always very important to convey this information. So what's the best way to show the depth of penetration? Well, you could eyeball it here. Like this is a good example where we could easily eyeball where the coherent signals from the GPR gradually fade into the more random signals of the background noise. But there is actually another way to do it that's a little bit more scientific, and this is where traces come back into play. Talked about GPR traces. So this is a type of plot that we call the average trace amplitude, or the ATA plot. And the ATA plot is a display of the GPR, of the signal levels, not just GPR signals, but the signal levels on the average of all the GPR traces in a line. And this is a standard part of Echo Project that you can do this. And so in this example, the yellow part is the background noise. The GPR signal is the blue signal here. That's the signal above the noise. Now, the depth of penetration is the point where the GPR signal fades to the background noise level. In this case, I mean, technically speaking, it'd be somewhere around 95 nanoseconds, but I think somewhere around 70 is where I'm going to be comfortable saying the depth of penetration is. Because we can see that the signals at 70 nanoseconds and more are very close to the background noise level. So I'd be really nervous about saying, oh yeah, I'm confidently saw deeper than I actually did. So we'd probably give that number to be conservative. So again, this is a standard plot, an ATA plot. You can do it with any GPR cross section, comes right up in Echo Project software. The other information we get from GPR traces is the frequency content of the GPR data. So this type of plot is called the average frequency spectrum, or AFS plot. Again, standard part of the Echo Project software. So the average frequency spectrum shows you the frequency content and the bandwidth of your GPR data. So along the bottom, we have the different frequencies from 0 up to 1200 megahertz. And then the red line actually depicts what we got from this particular data set. So in this example, if we look at about 50% of the peak amplitude, which is the recognized way of measuring bandwidth, the Noggin 250 data shows a bandwidth of about 250 megahertz from, if you look at it, from about 125 megahertz to 375 megahertz. Now, AFS plots allow you to understand your GPR better by plotting the frequency spectrum yourself and not relying on the system specifications. Some people have been known to measure their bandwidth at 5 or 10% of the peak amplitude and claim that as their system bandwidth. This results in crazy wide bandwidths. If we did that here, the Noggin 250 would have a bandwidth of about 850 megahertz, from about 50 megahertz here to about 900 over here. Certainly not the bandwidth that Sensors and Software claims for the Noggin 250 system. So while technically a measure of bandwidth, it's misleading because the bandwidth at frequencies with very low amplitudes is not usable in most cases. Okay, the last thing we're going to talk about is reporting. Now that we've visualized the data, we've added our interpretations and our insights to the data, the last step is to output something that we can deliver to our client or our audience. So let's talk about these reports. The first one is the PDF report, as I mentioned. So good old paper or PDF version of a report that gives you a title page. You can put images on it. And here's a short report just to show you the concept. And what I want you to note here is notice the first page here has photographs in it. So we've attached photographs, and that's why it's important that's why I mentioned to take photographs as you're collecting the data, because you want those action photos in your PDF report. The next two pages actually show screen captures. So those are by pressing the camera button on the DVL, on the data logger, as you're out collecting data, capturing those images that appear on the screen, and you can include those in your report very easily. And the last page is actual images created by the Echo Project software. So we've created a depth slice that we really like. We saved the image, we include it in our report. we create a cross section we really like, we save the image, we include it in our report. So with all these resources, with the photos, with the screen captures, and with the data processed with Echo Project and saved with Echo Project, we can make a very complete report for our clients. We can also generate KMZ reports, Google Earth reports, and the beauty of Google Earth is it's free software, so we can send it to our client. They can look at it. So in this example, we're taking our GPR survey, we're saving it as a Google Earth file, and then if you happen to have Google Earth on your computer, it will launch Google Earth and fly in and show the survey that you collected, the GPS paths, the pseudo grids, the grids, depth slices, anything that you've added to the data, as well as interpretations as well. So that's a standard report out of Echo Project and is very quick to produce. This example shows just a still image of utility interpretations added to zigzagging across an area. So we have two utilities crossing in this area and shown in the context of where it was collected. So a very powerful way of presenting that. This one, a depth slice shown at a gas station to indicate where the underground storage tanks are buried. You don't have to write a lot of words when you have images like this, when you present images like this. Even people without any experience with ground penetrating radar is going to understand that the red dots are probably objects in the ground that they're interested in. So it allows you to quickly show you the location of buried tanks simply and effectively. So one of the most powerful files from Echo Project is called the Project Report CSV file. It's a spreadsheet of all the positions of the interpretations added to the GPR project file. So columns of details include X, Y, Z, depth, longitude, latitude, elevation, GPR signal amplitude, etc., etc. So this boring file can produce a lot of impressive results. One of the things that allows is for the GPR data and the interpretations to be exported to third-party software programs. And let me show you some examples. So for example, GIS software. A lot of your clients probably use GIS software. And so here is the GPR CSV file opened in GIS software with the utilities displayed with the streets, in the context of the streets where they were collected. Another output of CSV files is visualization software. So here's a depth slice, which is actually displayed in third-party software, in this case called Surfer. We can take polyline interpretations. So if we take multiple polyline interpretations from multiple lines, we can create surfaces. And so in this example, this is actually the GPR reflection from the bottom of a lake. And so they took all the GPR data, they added a polyline interpretation to all the reflections from the bottom of the lake, and then plotted it in third-party software. And so now we can see in this lake, now I think there's a lot of vertical exaggeration here, but we can see the plot. So very powerful ways of displaying your data. We can also go to point cloud software. There's a lot of point cloud software which is basically free. And so we can save the GPR data into CSV files that can be easily read into point cloud software. And we can do these types of 3D displays. And we can also do sort of the curtain type display. So if you have a GPR line where you zigzagged across the area, you can display it like that. So this was plotted in point cloud software. Okay, 2 more slides, and I'm finished. What I want to mention is that we also have an advanced processing suite. So there's a suite of functions that you can, it's included in the Echo Project Suite software that gives you the ability to do more advanced processing. So things like instantaneous attributes to the data, migration, various filters, bandpass filters, deconvolution, high pass filters, low pass, median, and as well as a bunch of editing steps that you might want to run on your data. So that's available as a separate module in Echo Project. And the last slide is another module. This is a specialized one called Bridge Deck Condition Report. It's for taking your high frequency data collected on a bridge deck and analyzing it using the ASTM standard to look at the condition of the bridge deck. And what you're looking at is variations of the amplitude of the reflections from all the rebar on the bridge deck. And so where there's weak reflection from the rebar, that's areas that may have deterioration going on, and they're areas that should probably be checked. So with that, I am finished. I realize that I have taken the full hour, and I am going to hang around for questions.
Great. Thanks so much, Greg. One question I have is, if you apply an elevation correction, will that elevation correction also translate into looking at things like depth slices and in the 3D space?
Not yet. Yeah, I'm sorry to tell you that yeah, we would like to have depth slices with elevation on them, but we don't have that ability at this time.
No worries. Thanks. Yeah, good to know.
Okay. Yeah, one to add to the future. You can either go through our website, which is on the screen. You can also send an email to sensoft_service@spx.com, and we'll get that answered. Okay, question came up here. Can we talk about CMP War Module a little bit? Or was that perhaps featured in some other webinar? That's actually a good question. I didn't have time to include that one. I don't have the capacity to kind of show you that. I'm going to have to do that in another webinar. Okay, but if there's a very specific question you have about that, send an email, and I can, we can pop on Zoom or something, and I can take you through it if that's necessary. Okay. Oh, actually, one question here. I'm not sure if it was answered. Does Echo software compatible with all GPRs with various frequencies? It's compatible with all sensors and software GPRs. Okay, so, and we have antenna frequencies from 12 megahertz to 1,000 megahertz. So it certainly works with all sensors and software GPRs. Echo Project is not designed for our competitors' GPR systems unless you can convert their file format into our standard file format, which I know some universities have done that. You might even be able to find conversion software on the internet if you poke around enough. So if that's, hopefully that answers your question. Thanks for your time. I appreciate it, and hopefully you learned something new and saw something that you can take advantage of with your GPR system and the Echo Project software.